covalent, sharing. So metals and nonmetals do the whole transferring thing. I'm just magnesium's like, guys, I get rid of the electrons. You take them. If you want to leave and go off with somebody else, that's fine. You just take those electrons. That happens with metals and nonmetals. Because metals are willing to give up electrons, nonmetals are willing to accept electrons. What happens when you get two nonmetals together? You get two nitrogen atoms. Hey, I need 3 electrons. Give me 3 of your electrons. No way. I need 3 electrons. Give me 3 of your electrons. And there's this arguing. They need to share. Nonmetals are going to share electrons. And so these are the covalent bonds. And so we'll see that neighboring atoms are going to share some of their valence electrons, and in that way they can get an octet. So let's look at hydrogen and oxygen. So hydrogen has how many valence electrons? 1. And oxygen has how many valence electrons? 6. 1, 2, 3, 4, 5, 6. Hydrogen's a little guy. He's just trying to get 2. Oxygen's trying to get 8. So the oxygen can try to convince hydrogen to give up an electron, but hydrogen's not going to do it. So they decide to share. So they're going to share an electron with each other. Sharing electrons, just like sharing cookies with somebody, it brings you together. It creates bonds between people when you share a meal together, right? So they're sharing electrons. This creates a covalent bond. And when they're sharing, both of those electrons get counted by each atom. So this hydrogen says, oh, look, I have 2 valence electrons. This one that I had that I'm sharing with oxygen, and that one that oxygen has that he's sharing with me. Oh, this is so nice. Oxygen looks at this and says, oh, I can count this one as well because we're sharing. But is oxygen happy yet? No. There's these 2, 4, 5, 6, 7. Well, if oxygen can share an electron with one hydrogen, why couldn't he share an electron with another hydrogen? So let's bring in another hydrogen. So here's another hydrogen that has 1 electron. And he is willing to share with oxygen. So this hydrogen counts both of these electrons as belonging to him. My husband and I have 6 children. If you ask him how many children he has, he'll tell you 6. If you ask me, I'll say 6. But how many children in total are there? Thank goodness there's only 6, right? It's not 12. They do belong to both of us. We each consider them ours, even though they're shared between us, right? So these electrons are shared. Hydrogen considers them to be his, and oxygen considers them to be his. So now oxygen counts 2, 4, 6, 8. Got it. 8 valence electrons. This is a good place. This is why water has the formula H2O. Because when you get 2 hydrogen atoms and an oxygen atom together, they can share electrons in a way to become more stable than when they are by themselves. Any questions? Yes?
Is that represented by one line?
We'll see that we can represent it as a line, yeah.
What about the OH negative polyatomic?
Well, that's a polyatomic ion, and that is, we can also draw a Lewis structure for that, but we'll get to ions later. Right, but aluminum is a metal. It doesn't form covalent bonds. Why does oxygen need more when it already has 6? It wants 8. Pardon me? I mean, there's a scientific explanation, and then there's the silly explanation. The silly explanation is because he wants to look like neon. You know, Why did my oldest son wear a Hollister sweatshirt to school every day? Because he wanted to look like his friends. Why? I don't know. Oxygen wants to look like neon electronically, have the same number of electrons. So the scientific explanation is that when you have the s and the p orbitals completely full, that's like a low place on a hill. You roll the rock, and the rock goes to the bottom of the hill. It doesn't stop halfway down or go halfway up the other side. It stops at the bottom because that's the lowest potential energy. Having 8 valence electrons is like the bottom of a valley. Things roll down there, and it's more stable. So they want 8. Aluminum will work to get 8, but because it's a metal, it's going to transfer its 3 valence electrons instead of sharing them. So let me draw this again here. So we drew water like this. Oops. And we refer to these electrons as bonding pairs and lone pairs. So this is a bonding pair, because that's forming a covalent bond. Those are shared between 2 atoms. And this is a bonding pair. So those are bonding pairs. And then there are lone pairs. The lone pair is a pair of electrons, but it's just on one atom. It's not being shared between. Well, that's just a different color for this. So these are the lone pairs. And lone pairs become very important when we're talking about molecular shape. So we need to be able to identify the bonding pairs and the lone pairs. Drawing all these dots gets a little tedious sometimes. On my program here, I can choose a fat pen, and so I can just go ding, ding, ding and make nice dots. With a pencil, it gets real tedious, because if you just dot it on the paper, it's not dark enough to see, and so you have to make all these little scribbly circles. I hate that. So another way to write this, you can think of it as connecting the dots on those bonding pairs. So here's oxygen and hydrogen, and we have these electrons. And what we're going to do is we're going to connect the dots, and those are going to be bonds. So if you see a line in a Lewis structure, that is 2 electrons that are connected, like connect the dots. So a line is 2 electrons. It represents a covalent bond. Any questions? So I made you memorize that silly sentence, horses need oats for clear brown eyes, to help you remember the 7 diatomic elements. Lewis theory explains why they form diatomic elements, why they make molecules. Let's look at bromine. Bromine was one of those, right? So let's draw bromine. And how many valence electrons does bromine have? 7. 1, 2, 3, 4, 5, 6, 7. Is bromine happy? 7 valence electrons. In fact, it's very reactive because it's so close to getting 8. It's going to try to get an electron from somebody. Well, if you have 1 bromine atom, you probably have another one. And so here's another bromine atom. The other bromine atom also has 7 valence electrons. So what can they do to become more stable? They can share. So they will each share 1 electron and form a single covalent bond between them. It's like they're holding hands. Now they're just going to run around holding hands, and they just feel much better about life this way. Okay? Junior high girls always go into the bathroom with a friend, right? Don't go anywhere by yourself. But electronically, bromine is more stable this way because each of these bromine atoms has 8 valence electrons now. Hydrogen also exists as a diatomic molecule, doesn't it? Here's hydrogen. Here's hydrogen. They each have 1 valence electron. Well, if 2 hydrogen atoms get together and share, Now they each have a duet. Remember, hydrogen is a little guy. He can't handle an octet. A duet is as big as he's trying to get. But now he has two, and so it's more stable as a molecule than as individual atoms.
Is a hydrogen bond more, is it stronger than a covalent bond?
Pardon me?
Is the hydrogen bond stronger than a covalent bond?
This hydrogen bond is a covalent bond.
Are they of equal strength though?
Some covalent bonds are stronger than others, definitely. Some are stronger, some are weaker. We're not going to get into details like that. But covalent bonds versus ionic bonds tend to be stronger than covalent bonds. Sometimes atoms will share more than one electron with another atom. So let's look at oxygen. Oxygen is also one of the diatomic elements. So here's oxygen. No, I didn't want to draw it bold. Oxygen. How many valence electrons? 6. 1, 2, 3, 4, 5, 6. Not happy. Got to have 8. Well, let's see what we can do with another oxygen atom. This one also has 6 valence electrons. Well, what if they shared? Are they happy?
7,
No, now they each have 7. Oh, well, there's this other one hanging out here. What if we shared those too? It's kind of a weird looking drawing. But this is counting both shared electrons in each. So 2, 4, 6, 8. And the other one also counts the shared electrons. This is like a husband and a wife that have 4 children. They're sharing 4 children. So that's kind of a messy way to draw it. So we usually draw it like this. Oxygen, double bond. And then it has each oxygen has 2 lone pairs of electrons. So this is called a double bond because it's sharing 2 pairs. Single bond, sharing 1 pair. Double bond, 2 electron pairs being shared. Double bonds are shorter and stronger than single bonds. Any question?
Can you go back to that?
I can.
How come it's only, you're only showing 4, and not like, isn't it supposed to make 8? And obviously it's sharing 2.
So here these are the electrons, right? So when this oxygen looks at its situation, it says, well, I've got these 2 lone pairs. Where's my pointer? There, see, I made a face at it, and now it works again. 2, 4, and the shared electrons, this oxygen counts as all belonging to him. So 2, 4. So there's 4 shared electrons and 4 lone pairs, so he has 8. And this one counts 2, 4, 6, 8. So they count all the shared electrons. So what happens is, because of sharing, now it feels like you have more electrons than you actually do. You didn't gain any electrons. There's still only 12 electrons in that picture. But by sharing, each can have 8. Does that help? Yes? When do you put the electrons on the corner?
I've seen some Lewis-Dot structures where instead of being on one of the sides, they'll be on the corners instead.
I haven't seen those. I'd be interested.
Oh, I'm sorry. I was Googling it. No, maybe it's extra. Just I know.
Oh, like if there's more than 8?
That's right.
There are times when there are more than 8 electrons. We'll talk about that, and then you just kind of have to squeeze them in. But if there's only 8, then we do top, bottom, right, and left. Any other questions? Questions are good. So let's look at nitrogen, another one of the diatomic elements. So nitrogen and nitrogen. How many valence electrons does each nitrogen have? 5, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. How can two nitrogen atoms get together and each have an octet? There's going to have to be extra sharing, right? Share that pair, share this pair, and share that pair. So nitrogen has a triple bond. See, this is Jody, and this is Kirk, and there's James and Zach, and Tommy and Michael, and Emily and Andrew. We made a triple bond. We didn't do that on purpose. We were shooting for a double bond. By sharing, each of these nitrogen atoms can count 8 valence electrons. 2, 4, 6, 8. And this one also counts the shared electrons. 2, 4, 6, 8. Isn't that cool? So triple bond, sharing 3 pairs of electrons. We represent it as a triple line. And these are even shorter and stronger than a double bond. And we can see this by looking at the distance between nuclei. If we look at nitrogen-nitrogen bonds, it's a triple bond. The distance is 110 picometers. If we look at a double bond between nitrogen atoms, it's 124 picometers. It's longer. So sharing more electrons pulls them together. Because nitrogen has that very short, very strong double bond, it's not very reactive. So nitrogen is a pretty inert gas.
So for the test, are we going to have to remember what falls on the chart? Like, are we going to have that covered? Like, do you know how many valence electrons?
The group numbers will be on the chart.
Oh, okay.
Yep. In fact, I intentionally picked a chart to give on exams that has both sets of group numbers. Because I don't like the 1 through 18. I like the other ones. Any other questions? You can't do this without a periodic table.